Alright, I'm sorry we didn't get to the last part of class today, so I'm making a video about one more example of graphing rational functions. And in this third one, something a little bit different is going to happen. And so we've got f of x is equal to x squared minus x over x plus 1. And I usually think it's a good idea to factor expression before we try to analyze it. And some immediate things that are the same as before is we've got a vertical asymptote at x equals -1 because that's the zeros of the denominator. We're not going to have any horizontal asymptote because the numerator outgrows the denominator as x gets really big because the numerator's degree is bigger than the denominator's degree. So we have none of these. But it turns out that there is another asymptote for this rational function, and it's something called a slant asymptote. And the way you find the slant or the diagonal asymptote for a rational function is you do either synthetic or a long division based on whichever actually works. So in this case, our denominator is x plus 1, so we could do synthetic division. And so I'm going to put the 0 of the denominator in the box, label the numerator coefficients, and do synthetic. So bring down the 1 times the 0 gives me -1, add together gives me -2, times the 0 gives me 2, add gives me 2. And so we get that this has a remainder, and we have that f of x, which was x squared minus x over x plus 1, is going to be the same as these two parts of the expression, x minus 2 plus a remainder, 2 over x plus 1. So this part here, the quotient, is going to give us our slant asymptote. And the reason why this is an asymptote is that this little part here is never 0, but it's always kind of there. As x gets really big, you've got this small value here. And so our function is pretty close to x minus 2, but it's never quite on top of it. So as x gets big, we're going to find that our function is going to get closer and closer to x minus 2, but never quite reaching it. So it's another type of asymptote. It's what's called a slant asymptote. And you'll get slant asymptotes whenever the degree of the numerator is 1 bigger than the degree of the denominator. Which makes you wonder, and I'll let you think about this, what if the degree of the numerator was 2 greater than the denominator? Let you think about that on your own. So, alright, so what do we do with this? Well, if I was going to start making the graph, here is the information that we would have. We would know that we have a vertical asymptote at -1. We also know at this equation of this line x minus 2 gives us another asymptote. So I'm going to plot the y-intercept here at -2, then use the slope of 1 to plot the rest of it. So up 1 over 1, up 1 over 1, and now that's going to give us the outline of what the other asymptote is. And so now it's a matter of finding some more points to actually get the where the graph is. We know where it's not. We know it's kind of around these lines, but we don't know exactly where it is. So let's find the zeros. The zeros of a rational function happen when the function is 0, and the only way a fraction can be 0 is if the top is 0. And so that means x times x minus 1 must be 0, or x has to be 0 or 1. So we know that at 0 we're going to have a 0, and at 1 we have a 0. So those are kind of close to each other. We could also find the y-intercept, which isn't going to be very interesting, because for the y-intercept, we'll plug in zeros for all the x's, and we get 0 over 1, or just 0, which lies right on top of the 0 because it's at the origin. When you have an x-intercept of 0, you also have that same y-intercept. So we've got these 2 points here, And if we know that we have to hug this vertical asymptote, and we know we're either going to go this way or that way, it seems pretty likely that we're going to have to go up. We can check more points to verify. And I'm also pretty confident that we're going to go down and then come back up and hug this way. So we've got kind of this whole region taken care of now. So now the question is, what do we have to the left of the vertical asymptote? And to figure that out, we're going to try a value to the left of it. So I'm going to try -2. F of -2 is going to be the same as -2 times -3 over -1, which I'm getting to be -6. So at -2, we have a value down here, 3, 4, 5, 6. So right about there. And based on that, that should be enough information to make us think that it's going to hug that asymptote as well as this one. So just like our other asymptotes, when you have a slant asymptote, your functions are going to need to hug them. They just happen to be on a diagonal this time instead of a vertical or straight line. So that's a pretty good graph of what's going on. Let's talk a second about the domain and range too. The domain is going to be all x values except for at -1. So we can write that one of two ways. X is not -1, or we could write it in interval notation, all the numbers from -∞ to -1, union with all the numbers from -1 to infinity. For the range, it's a little bit trickier because we don't really know how low or high the graph is going here. So if we took out our calculator, we'd find out that the minimum value is going to be at about, I actually don't have the x-coordinate, but I found that the y-coordinate was about -0.1. And I found out that the top value here on this function, it goes all the way up to some other x-coordinate that I didn't find, but it went as high as -5.8. And it doesn't get any y values in between there. So what that means for the range is we get all the numbers from -∞ all the way up to -5.8-ish, combined with all the numbers from -0.1 all the way up to infinity. And so that's how you graph a rational function if it's going to have a slant asymptote. And once again, it'll have a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator.